We're going to talk about carbon-13 and resonance and how that relates to organic chemistry. And trust me, that is something that is going to be very valuable to you. And so it's often called carbon NMR or CNMR or carbon-13. There's a variety of names for this topic. Okay, so the NMR stands for nuclear magnetic resonance. And it's a cool concept that is actually the basis of MRIs. So if you've ever heard of that, this is called magnetic resonance imaging. And we'll talk about this, but they're really the same thing. But people will not, they would never submit themselves to something called nuclear magnetic resonance because of the word nuclear. They think it means radiation, but it doesn't in this case. It just means nucleus. But when we talk about, if we called it a magnetic resonance imaging, then they'd say, oh, well, that's not so bad. I can do that. Well, that's fine. It's the same thing. All right, so let's talk about what is going on with carbon-13. And we have three versions of carbon. There's three isotopes of carbon, carbon-12, 13, and 14. If you remember, carbon-12 would be written like this. And so the concept is that the mass number of 12 minus 6 protons leaves us with 6 neutrons. And if I had carbon-13, right, the same idea, but this time it has 7 neutrons, and then without worrying about the math, carbon-14 has 8 neutrons. Carbon-14 is unique because it is radioactive, not high level, but it decays from carbon-14 into something else, probably carbon-12, which is more stable. Okay? And it turns out that 1% of all carbon isotopes is carbon-14. And so when we have a situation, for example, when there's a branch or some kind of live organic matter, that 1% of that is carbon-14. Okay? That's just, when things are grown, that things are produced, carbon-based organic compounds, substances, whatever, 1% of them are carbon-14. And what happens is that over time, 50%, right, decays, and that takes 5,380 years or something like that. It's pretty close. And then if another half-life passes, in other words, half of the remaining carbon-14 disappears, then we know that another 5,380 years have passed. So now we know that if we find something that is 25% of the original 1% carbon-14, right? So 1% became 50%, became 0.25%, whatever it is. This amount of that's 2 half-lives, and so we know that that has been it's like 11,760 years have passed, just based on the remaining amount of carbon-14. So that's carbon-14. Carbon-13, why is that unique? It has magnetic properties. And this actually is going to be very relevant to what you do in organic chem. So I want to take you a little walk through electromagnetic concepts here. So when we talk about electromagnetism, right? The story goes that Michael Faraday was one of the fathers of electricity, if you will. I know Ben Franklin had the kite. That's great, all that good stuff. But the basic idea was that there was a battery of some sort here, positive and negative. So we'll just kind of have this coil here, and we'll make this coil like that, and then we'll make it come back. Okay, so here's the positive, here's the negative, right? We'll make these little terminals there. Okay, what happened? Somewhere on this laptop, actually, was a compass, right? So we'll draw that little compass here, but this time I'll draw it with the bird's eye view. Here's north, right? And so on. There we go. Okay, so here's this little compass. He runs a current. Now he knew he was running a current through it, right? And so the electrons are going through this wire, and it deflects. This north pointing compass needle deflects. Now maybe it went toward the coil, maybe it went away, it doesn't matter. It changed, and when he took the leads off of the battery, then it returned back to north, and so on. So now he says there's a connection between electricity and magnetism. That's really all that's going on. You've seen this before, I believe. If I take a north-south magnet, really how it works is this. If I have a coil here, so we'll just run a coil like this. We're going to take a magnet here. We'll call it a north-south magnet, and we run it through the coil like that, right? So now the magnet goes here and back. It has to have flux. It has to have a motion is what we're really saying. If it goes slow, you don't really notice it. But what it does is generates a motion of electrons. It generates a current. It produces electron motion in that coil. And when it pulls back, the electrons go the other way. You see? So that's called alternating current, which makes sense, going back and forth. And so we call that AC, right? And here in this battery, because it was direct current, right, we call that DC. So now AC and DC, named for a great rock band, but also for the fundamental versions of current motion. All right, so how in the world does AC/DC have anything to do with carbon-13 resonance? Okay, so carbon-13 NMR, nuclear magnetic resonance. Carbon-13, we're going to draw like this. We'll draw a little 13 in there. Okay, so we're going to assume that by virtue of its spinning electrons, for example, right, that there's some kind of spin, and that's what the physicist and chemist will refer to, that there's some kind of a spin, right? And because of that, we can now look at this as some kind of a magnetic situation. Really it is. I mean, there's a magnetic spin by virtue of the electrons spinning around. We can say that that would account for carbon-13 having magnetic properties. Carbon-12 and carbon-14 don't do this, and it all has to do with the idea that there's 7 neutrons, from what I remember, because it's kind of unbalanced and has to do with the electron configuration arrangements and whatever. We're not too worried about that, but you get a little magnet here. Okay? So what we have to remember, though, is that if we have some kind of bodily tissue like muscle, or we have a chemical, not all of the carbons are exactly the same. Okay, so let's just draw that. Let's say that these carbons are acting like little magnets, okay, doing their little carbon-13 thing, being their own little magnetic selves, okay? And so we could just assume that each of these represents a north magnet, okay? So what happens? All right. What we do now is we assume that these have, some of them have strong magnetic fields, and we'll talk about that more later on, but we're going to draw a good old-fashioned cartoon magnet from back in the day. We're going to assume that we have this horseshoe magnet. We don't really use a horseshoe magnet, but for now, that's going to be what we're going with. And we turn this magnet on. And so what's the response? All of them are going to tilt, right? Everybody is just going to line up so that their magnets all align, right? So we can say that all of the north poles tilt that way. Now we're getting close to this idea of magnetic resonance. Let's remember this. Nuclear, these are carbon-13. magnetic because they have this electron spin, and so they produce a magnetic field. Where's the resonance? Okay, what happens is when we produce this large magnetic field, then we turn it off. Turn it off. And what happens is all of them drift back. They drift back to where they were, just like that compass drifted back. So this guy might have tilted a little bit back. This guy might drift back a lot, and so on. And that's when we pick up the energy. There's a radio frequency that comes off of that. Okay? Let me explain that again. Let's do this again. Carbon-13 is an isotope of carbon that has magnetic properties. All carbons have electrons spinning around them, but carbon-13 is unique. It has magnetic properties. Okay? Then we have carbon sitting in a sample of ether, or we have carbon sitting in a sample of esters. I don't know. Doesn't matter. They're all going in their own direction. And some of them are going to be different from each other. Not all of these carbons are exactly the same. Some are attached to oxygen. Some are attached to a double bonded oxygen, whatever the case may be. Okay? We put them in the presence of a very strong external magnet, and all of a sudden these guys align. They point. Okay? But when we turn that magnet off, they drift back, and that's when we get their readings. That's when we get energy that tells us something about those specific carbons. Okay, so now that is where we get nuclear magnetic resonance. That's the whole idea. Call it carbon-13 or CNMR. And sometimes you see it as small case. Not a big deal. Okay, so that's pretty crazy stuff. Well, we're not totally there yet. There are some other concepts here. Okay, what we have to talk about is insulation, or what is called shielding. Now this is very interesting, and the more you get into college chemistry, you're certainly going to have to understand this better, and it is worth it. The more you understand this as you go in, the better. Okay, so let's just talk about this. Let's take our carbon-13 and we'll just pick a carbon right here. All right, so you know that carbon-13, right, just 13, that's all we need. This carbon-13 has a magnetic field associated with it. Okay, and if we surround that carbon with hydrogens, okay, it kind of has what's called an insulating effect. Right? In other words, carbon is able to maintains its magnetic field, or its magnetic force. So we'll go with magnetic field for now. Okay? That's insulated. These hydrogens, because they also have electrons going around them, they can protect that. Okay? And this is very typical of alkanes and so on. All right? So what I'm going to do is show you now. Here's this great big external magnet over here. All right. And what do we say? Well, this carbon-13 would tilt, right? Let's hold off on that for a second because I want to show you something else. We're going to give you another extreme case now. What if this time we have a carbon that is going to actually have an effect on the electrons? Okay. One of the things you have to remember is that oxygen is very electronegative. Right? That means it's an electron hog, and basically it's stealing electron density. But that's why you had to learn about electromagnetism, because what happens essentially then is that the electron density of carbon is really pulled away by that oxygen. That has an effect on its magnetic field. So now we can go back up here, and here's carbon. Okay, And here's the way I do it. Great, big, huge, strong magnet, right? But if you've had your magnetic powers pulled away, right? Because you have the electronegative oxygen hogging your electrons, then what we could say is you have this teeny tiny skinny little magnet like this, or we could do it like this. It doesn't matter. The idea is that you have a much smaller magnet because this electron density pulls that away. The best situation you could have for carbon to have its magnetic field is to have it insulated. So these guys are not going to they're not going to take electrons away from carbon nearly as much as oxygen, right? In fact, these guys are positive, so they're not in the business of stealing electrons anyway. So when carbon is surrounded by these situations of hydrogens, it's going to have a very strong magnetic field. And then there's this. This guy is an electron hog or very electronegative, and so now we can now go back and look at these guys here, okay? And if you remember, I told you that one of these might have shifted back, right? Might have shifted back more. That guy right there. And then this guy shifted a little bit. Well, this one that shifts a little bit, right? He was probably well insulated because a big magnet is not going to have an effect on that kind of carbon. It's strong. It does what it wants. Put it in a magnetic field. Hey, it's not going to drift. I'm a big, strong magnet. This guy, if this carbon-13 was attached to a double bonded oxygen, he's not much of a magnet at all. You turn on an external magnet, and man, that thing's going to flip. And as soon as you turn this magnet off, it drifts back. Okay? That's just the concept to show you how that works. Okay? Now, I know we're going to need more examples here, but that's a start. Let me show you what a carbon NMR a spectrum looks like. Okay? So let's look at our first carbon NMR spectra. Spectrum. Okay? It's going to be different from an infrared IR spec. Okay, it's going to be different from an IR spec. Let's start here. Just draw this general idea, and we put 0 over here. And now it's called parts per million for reasons we can get into later on. But it's called ppm, parts per million. Okay. And then for carbon NMR, this goes up to about 210, 220 parts per million. Okay? And we can talk about this here. This is a radio frequency or whatever. I'm not too worried about that right now. Okay? So what do? We actually see these things called peaks. Okay? Maybe we have 1, 2 here, and then 1 here, and then something like that. Okay? And those actually, just by virtue of where they are in proportion to each other, that tells us a little bit about the carbons that we are working with. And by that I mean these guys here are probably carbons that are attached to a double bonded oxygen. Okay? Here you might have something with a single bonded oxygen, and there could be others. We could have this situation too, right? In other words, these are also electronegative, stealing electrons here. But now these are most likely that situation where we now have a carbon that is either surrounded by H's like alkyl, alkane, right, single bonded, or we might have a carbon-carbon bond. And we could have other situations. We have a table for this called a shift table. This is called the shift, right? These numbers here tell us how much the magnet drifts back into its regular shape. Okay? So I know that's a very nebulous concept of what's going on, but let me show you one more thing that's going to get us ready for the next video. All right, let's draw something like this. Okay, So here we go. That's a carboxylic acid. Perhaps you've met, right? 1, 2, 3, 4. So that's butanoic acid. And there's a couple things that should stand out. And so what we do, this is just a warm-up because we're not going to do all of that now, but what we typically do is label the carbons with letters. That way they're easy for reference. And we just compare them to what they would look like on the spectrum. Okay, so now I have this situation here. And the question is, how does this help? Well, first of all, we have 1, 2, 3, 4 distinct kinds of carbon, which we will talk about later. There's 4 distinct types of carbon. And so what we're going to find is we have 4 distinct peaks on the spectrum here. Now this guy here, this D, he's probably going to go around here. Now I told you this is about 210. Okay? So that kind of carbon is most likely going to be down here. We have specific numbers for this. It might be 178.3. I'm just showing you the basic ideas. Okay? This carbon here is not even close to being influenced by any oxygens. It's surrounded by hydrogens because if we look at A a little bit closer, right, you have a carbon here. That's really what carbon A looks like, because it has 3 H's. What we would say is that's well insulated. Okay? And it's going to seem a little crazy, but carbon A is probably down here. And I'll tell you a little bit more about that in a minute. Okay? Now, we look at B and C. What we're going to start talking about later on is that this carbon here is actually somewhat influenced by the presence of that oxygen in the neighborhood. And if that's the case, the electrons don't leave that carbon, but they start to pull away a little bit. And when those electrons pull away from this carbon, it loses its magnetic field. And so it he's going to be closer to this oxygen. Now let's remember, this is carbon D, not this oxygen, this carbon. This is carbon D. This is a weakling of a magnet. Why? Because all of this electron density is being pulled away. And so carbon D doesn't have a chance. Carbon D doesn't have many electrons around it. They're all pulling towards the oxygen. So when he tries to act like a carbon-13 magnet, can't do it. Why? He doesn't have any electrons. He can't do it. So this is a very weak magnet. We could just draw a teeny tiny little guy here, okay? But this carbon A, hey, he's totally surrounded by hydrogens. Nothing's gonna steal his electrons, right? He's not even close to this bum, right? So carbon A is going to be somewhere down here. Just remember, there's no actual magnet here, but if I drew this, it really helps to think there's this external magnet here. And this magnet here, big, strong, solid, reliable, okay? He can withstand being close to this external magnet. This guy, if he stands a chance, he's going to have to be far away from the magnet. We talk about that being further downfield. Okay? Now, this is upfield, close to zero, upfield. Let's talk about these other two and then we'll do the summary here. Well, this carbon is losing some of its electron density to that nearby oxygen. He's got a weaker magnetic field, so we're going to put him over here. Okay, so he's not totally as strong as this guy, not as weak as that guy, so we'll just draw something in between. Okay, there you go. All right, but look at this. This B. Well, he's losing a little bit, right? Some impact by being near oxygen, but not as much, right? So B is actually going to be somewhat stronger of a magnet. So it turns out B would be positioned here. It's not always alphabetical order, folks. Okay? but this carbon is represented by that peak, and we could draw a magnet that's proportional between these two, and we're not going to do that. Okay, let's go back. Let's talk about what we just did, because you have got to understand carbon-13 resonance. Okay, the idea is that it's called nuclear because it's a carbon-13 nucleus, and they have magnetic properties, but that's only true about carbon-13. Okay, and even though 1% of all carbon isotopes is actually magnetic, that's all we need, because if you think 1 mole of a substance has that many carbon particles, so we're okay. We don't need that many in the first place. Okay, but the idea of electromagnetism helps here, because that's really what's going on. You spin an electric current, you get a magnetic field. All right, and so that's what this is. Okay, it turns out that if we have magnetic resonance imaging, if somebody gets an MRI, they actually put your body in a great big magnetic field. And some of the carbon-13s are in muscle tissue, some are in kidney tissue, or they're in bone tissue, whatever it is. They're different. And so they're little magnets that are just different from each other. They turn on the magnetic force field, right? Turn it off, and when these magnets drift back to where they were, we get these little energy frequencies. Okay, and then we measure those. Okay, now why would some carbons be different from each other? Well, if you can protect that electron spinning around that carbon, right, that electron current, we will say, if you can protect that, then you are protecting the magnet. Okay, and hydrogen and other things are really good at that. They don't mess with the electrons. Carbon can be the strongest magnet it can be. Okay, but you put carbon around an oxygen, it's going to start stealing electron density. And what happens? You steal that electron density, you steal that magnetic property. Okay, so now you're going to get a skinny magnet or a small magnet instead of a big, fat, juicy magnet like that guy. All right, so what do? We can measure these things. And what happens is when we measure the energy that comes off of that magnet as it returns to its original position, okay, when we get peaks down here, it means we must know that there's a carbon in that structure that's near or is attached to a double bonded oxygen. Or maybe we have a carbon in this region, we have measurements, that we know that carbons with single bonded oxygen and chlorines would be in here, and then we would have these guys. These kind of carbons are attached to hydrogens only, well insulated, not being robbed of their electrons. All right, so here's a very simple example. If we took butanoic acid, these carbons are interesting. This guy, D, is directly attached to the oxygen, loses his magnetic or electron field, most of it, so he loses magnetic properties. We need to put him where weak magnets go, far away from this imaginary magnet here. It's not really there, but we act like it is. Okay, this carbon here is in the vicinity of that oxygen, and he is also going to lose electron density for a couple reasons. One is because when this carbon lost electrons to oxygen, he became slightly positive, and so the process continues. So this carbon is in the neighborhood, and it is impacted. He loses some magnetic field. He goes here. Okay, and finally, carbon A, far away from all of this mess and well insulated by hydrogens, doesn't lose its magnetic field. It's big and strong. We got this guy. These kind of carbons we put near zero, which is essentially saying they are not affected by the strong external magnet. So those are the basic concepts of carbon NMR.